Hello, in this video, my purpose is to illustrate what you already know about linear functions from all the work we've done up until this point. We're going to explore linear functions a little bit further so we can learn some new things, but let's start with what we should already know. First of all, we can start by being given a rate, and if that rate is constant, then that refers to a slope of a line as much as it refers to a rate or speed. So we start with driving at a 50-mile-an-hour speed, and we recognize that if we drive for 3 hours, that'll be 150 miles. Notice the dimensional analysis here that we have 50 miles per hour times 3 hours, and that gives us 150 miles. Miles per hour times hours, the hours seem to cross out or cancel each other out, and we end up with just the mileage. 7 hours, 50 miles an hour times 7 hours gives us 350 miles, and so on. So what I recognize is if I multiply any number of hours times 50 miles an hour, I'll have 50 times however many miles, however many hours multiplied by 50 will generate the number of miles that I will have driven. So basically what we're doing is we can take a constant rate of change and turn it into a linear function simply by multiplying by the independent variable of the rate. The change in x, if you will. So if we take 50 times the number of hours, it gives us a distance. We saw that manifest itself here when a plant grows at 2 centimeters per week. Once again, that is a rate. We'll assume it is a constant rate, and if we actually multiply centimeters per week times the number of weeks, weeks will divide out, and we're left with 2x centimeters. So we have a rate, centimeters per week, we multiply that by the number of weeks, and that gives us the total number of centimeters. So here the function is the same as the one before. We multiply our rate times the independent variable, and that gives us our dependent variable. Nice and simple. Notice the rate of change remains constant no matter what we do. Anywhere along the line we will see a 2 centimeter increase for a 1 week span. So this is another week right here, and this is a 2 centimeter increase, and off we go. If the rate is $3 per foot by rope, then we see the same dimensional analysis. We have $3 for every 8 feet. We multiply that by the number of feet we purchase, and that's going to give us dollars. So $3/8 times the number of feet of rope. Notice the graph ends up being the same. We have the rate of change or slope times the independent variable gives us the dependent variable every time. Notice the rate of change can be found. This time it's 4 feet for $1.50 because it's 8 feet, $3, and so on. Now, what makes this function different is we have a height of a plant and it's growing constant rate of 2.5 centimeters every week, a half centimeter every week. Then what makes this different is the plant is starting at a 2 centimeter growth, or a height rather. So that changes my function. I still have the rate, which appears to be a half centimeter every week. So that's my rate times the independent variable, the number of weeks. That'll give us total centimeters, plus the additional 2 centimeters we started with. So our linear functions have just gotten now more sophisticated because we can start somewhere at a fixed value and then add or subtract a rate times an independent variable to get total whatever it is that we're looking at. So the height is equal to 2 centimeters plus an additional half centimeter times the number of weeks that it's had to grow. So once again, we can see the line behaves the same way. We start somewhere and then we represent our rate of change using the triangle, and that creates a line. Test tube, same exact situation, except instead of plants growing, it's test tubes being full of water. This starts with 3 cubic centimeters or 3 milliliters of water, and we're adding 0.4 cubic centimeters every minute. So each minute we go another 0.4 cubic centimeters added to the existing amount of water of 3. So once again, we still have our rate times the independent variable, but we add that to an existing volume to give us our total volume. So with all of this in mind, we can experience that linear functions can be spotted just from looking at their equations. Here we have a fixed starting value, a constant rate of change multiplied by the independent variable to get the dependent value. Once again, a rate of change, we have a fixed constant value. This is a linear function. Here, it might not look like it at first, but if we distribute the 2, we get 2x minus 3.5, which, again, fixed starting value and a rate of change. These functions over here are all not linear, here because the variable is an exponent, here because we have a squared variable, here because we will have 2 divided by x, not multiplied by, square root, and whatever 1/3 power means. Neither of these functions, not one of these functions, would be linear. So what? Well, if you look at all that work, all the stuff that we've learned that the form of a linear function can go in one of these two ways. We could either start at a constant value and increase or decrease at a fixed rate, or we can have an increase or decrease at a fixed rate plus a fixed starting value. I like this one because it makes more sense when you read it. The value of the function starts here and increases at that rate. So anytime you see a linear function, if there's already context, it should be easy to understand as soon as you put it in context. The monthly cost to ride the bus, starts at $21 and increases 50 cents for each number of rides that you take. Even if you have a function that's in generic form, we could say y starts at 10 and drops by 2 for every increase of x, because that's drop 2 for every 1, rate of change in y over change in x. Or we could impose our own context, and especially using money and time. We can actually start here with, I have the money in my account starting at $10, but I'm going to spend $2 every day. So that way I can understand what this function is trying to tell me by inventing a simple enough context to follow. So with that in mind, we could follow a specific procedure to graph a line. If you follow these steps, you restate the function in a context, it'll make something that you could actually think about and reason about so that it's easier to follow. Then identify the slope and y-intercept, and you can improve that by adding the context. Make a quick sketch of what the graph should look like, so tell me that you can already imagine where the solutions to the equation will lie. Identify two solutions. One of them is the y-intercept, that's a freebie, and then one other point along the line using your slope. After the line is drawn, find a third solution to verify that you've done all your work correctly. So this is how we support our answer, this last step. This is what it would look like in the aggregate if you put all the pieces together. I would have, starting with the equation, I invent a context. I had over $4 2/3 in an account. I spent a quarter every day, or $1 every 4 days. So I have a context. Then I could actually, make a quick sketch. That is, I start with this much money and spending a quarter a day. I'll still hang on to my money for several days, so it's not going to be very steep. Identify 2 points. Now this work here is pretty sloppy because I was doing this with writing this with a mouse. So I thought it would be worthwhile showing you a better example, graphing this line. So here's where you start. You start with the context, and this time I'm going to talk about temperature over time because I'm optimistic. I want temperature to increase. But I will say temperature in degrees Celsius is a function of time and days. I'm just making stuff up. I want it to be semi-reasonable within the context. Anyway, the second thing says identify the slope and the y-intercept. You start off by identifying the y-intercept exactly as it should as a coordinate set. You could even show off and say, look, at 0 for x, we end up with 8 for y. That's why the y-intercept is 0, 8. Even better, add to your context with this new information. That is, the temperature today was 8 degrees Celsius. Starting temperature, 8 degrees Celsius. Then identify the slope. Slope in this case is 5/3. You can see that right here. Now I'm going to pause and just say, the slope is not 5/3 x. 5/3 x is not the slope. The slope is 5/3. When we multiply the slope by x, it produces a new y value. So remember, if the slope is not 5/3 x, it's just 5/3. So change in y, 5 for every 3 x's across. Put that in context. My temperature will increase at a rate of 1 2/3 degrees Celsius per day, or in other words, 5 degrees Celsius every 3 days. So I would get a graph that looks like this. Now I made the steepness more than 45 degrees because the slope is more than 1. And I have at least enough detail to know that 0, 8 is a starting value. Now, the thing that it says next is to identify two solutions to the equation. This is really easy to do because we're going to start with 0, 8. That's our y-intercept and starting value. And then I'm taking my statement after I identified my slope. My slope said we're going to go up 5 degrees after 3 days. So I demonstrate how f of 3 indeed gives me 5 degrees more, or 13 degrees Celsius. So, to make the graph, I use a centimeter ruler and I mark off a scale that fits with the kinds of numbers. We need to go up to 13 and beyond, and we need to go at least up to 8 degrees for starting. So, I plot the point 0, 8, I label it. Then I plot the point 3, 13, and I label it. I draw the line. that goes through those 2 points. Now this, once again, represents all the solutions to this equation in context. However far I want to go away from today, I could predict the temperature assuming that this rate remained constant, which is wishful thinking this early in November. Anyway, to finally support my work, it says, after the line is drawn, find a third solution. I'm just going to go with this trend. I'm going to go 3 days more. I should be another 5 degrees hotter, so I should be at 8 plus 10 or 18 degrees. So just checking it with the algebra. F of 6 turns out to be 18 as I predicted, and that point, when I find 6 and follow it up to the graph and follow it over, it lands directly at 18. So my line is drawn appropriately. It's now going to be an accurate picture of all the temperatures for all the days ahead, again in some fantasy world. Thanks for watching. I hope this was helpful. Have a good day.